All right, gang, Math 6620. I just want to continue on multiple regression. And I think from the previous video, I hope I impressed upon you that once you understand simple linear regression, adding more predictors moving into the multiple regression world is a pretty simple transition. One part of this that gives students uh, some difficulties, though, is including a categorical predictor, easy for you to say, with more than two groups, as we have with gender. And if we look at, let's just examine district, and we can see that we have 29 from District A, 37B, 37C, and of course we can get our percentages, so 28.2% from District A and so on and so forth. Okay, now if we wanted to include District A, District B, District C in our model, I think it's going to be easiest to just step back and take a look at what happens just entering it alone. And then I'm going to transition into a model that has exam, score predicted from anxiety, gender, and district. But I just want to look at district just for a second to give you an idea of how dummy variables are handled. So dummy variables are included when we have a categorical predictor with more than two levels. So we have district A, B, C here, so clearly we need dummy variables. The first thing we need to do, and I'm going to just read level this as district, is or rename it as district, is to re-level and choose a reference district. So what's going to happen is we're going to have K equal 3 levels here. We're going to have K minus 1 predictors in our model, and I'll explain that more in just a second. So we need to decide which district we want to be our reference. Now, typically that will be driven by uh, a research goal, but in cases it's not, you might want to go with the district with the lowest number of participants, or you may want to go with the one with the highest. If really there's no education research reason, motivation, I would probably just go with the district with either the largest or the smallest. So I'm just going to choose District A. Now, what's going to happen because of the way that we interpret coefficients? Remember, it's holding everything else constant in our model. When we increase our value 1 unit in our predictor, the predicted value of the dependent variable changes, whatever the coefficient is. The problem with having a categorical variable with 3 levels is we can't increase from like 0, 1, 2 with any meaningful interpretation as we can with a quantitative predictor like ACT. A 25 to a 26 and 26 to a 27 makes sense. 0 to 1 and then 1 to 2 makes no sense when we have categorical predictors with more than two levels. So the solution is we create dummy variables and we create a reference category, in this case District A. Now when we run our model, what we're going to have is we're going to have two coefficients. We're going to have District B compared to District A and District C compared to District A. In both of those, District A will be considered 0, and District B in 1 will be 1, and District C and the other coefficients will be 1. So let's see how it plays out. It's kind of cool. So we create our model, and we're going to construct a linear model on exam predicted by district. Well, I recoded that, didn't I? And I want summary model. And you can see exactly what happened. Again, that coefficient, District C to District A comparison. This coefficient is District B to District A comparison. Again, it just shows how important it is to well, have a reason for selecting one district as your comparison group. What I typically do, I run into this a lot with race. So if I'm in a school district that is predominantly white, I'll typically choose my reference category as white. If I were looking at maybe a political poll, political data, if and let's say I had independent, moderate, libertarian, Republican, Democrat, if I was examining data for Fox News, I would probably set my reference category to Republican. If I was analyzing data for MSNBC, I would probably set my reference category as Democrat. Again, we kind of search for those quote unquote artificial reasons, superficial reasons, if you will, to set a reference category. Now, what we get is something interesting. We get that in comparing exam scores across District B to District A, we do not have statistical significance. Remember, anxiety and gender and all that hadn't even come into the equation yet. We're just looking at District A, District B, District C. District C and District A are different. So my interpretation here would be, let's just do, for example, District C. So we would say when controlling for the District B to District A comparison, District C students score 19.256 points higher on the exam than students from District A. Now, how do I know the District C students are scoring higher than District A? Because I set my District A students as 0. So again, the interpretation of the coefficient, we go from 0 to 1. So as I go from 0 to 1, I go from 19 points higher. So my 1 is 19 points higher than what I classified as my 0. And the interpretation would be just about the same for District B. I would say we're controlling the District A, or I'm sorry, the District C to District A comparison. District B students scored 2.689 points higher on the exam than students from District A. Now, it should be no surprise that if I look at exam over district and look at the mean, it should be no surprise that District C is going to score higher, hence the significance. And notice that District B and District A are pretty close, hence no significance. Now, have a student ask me all the time. They will say, "Well, oh, this is cool. I can compare District B and A to District C and A. What if I want to compare District B and C?" Well, then come up here. Went too far. Come up here. Change your district comparison. Run your model again. And if he said B is your base group, then you can compare District C with B and District A with B. And again, notice that District C compared with District B is statistically significant, whereas District B and District A are not statistically significant. Now comes the fun stuff. Let's create a new model, and we'll look at exam score over anxiety plus gender. Well, actually, I'm getting ahead of myself. I need to set my base for gender. So I want to re-level gender, and I want my reference to be equal to male. So I'm going to run my new model. So I want exam plus anxiety plus gender recode plus district summary new model. So what do we know? We have tunnel vision, don't we? We look at our predictors. Anxiety is still a statistically significant predictor of exam score. Gender is not statistically significant when controlling for the impact of anxiety and district. And notice that District A and District C are no longer statistically significant when controlling for district controlling for anxiety and gender. So some of the difference in District A, B, C specifically, District C and District A, their exam score difference must be contributed or attributed to some way anxiety or gender within the school, because again, they're no longer statistically significant. So where would you go from here? Well, you did the same thing we did before. You would go through your, test your independence, multicollinearity. You would go through your case-wise diagnostics, and you would test for the normality of the residuals and equal variance. So exactly the same thing as before. Now, what I would probably want to do with this model is I would probably want to perform a stepwise regression model, so a backward elimination. So what a backward elimination model is going to do, and something you can do in R, it would first probably get rid of the District A to District B comparison because it has the highest p-value. It would reassess the model. If eliminating that variable improved statistical reliability, then it would create that as a new model, calculate the coefficients and the p-values. It would then take the coefficient from the remaining coefficients predictors, and it would remove the predictor with the highest p-value and repeat the process. Where it came down to a statistically reliable model, statistically improved model with the least number of predictors. So I will probably yeah, I could probably do that right now. I'll probably do this in the next video. Let's just see. I forget. We can create a backward, and I can do step. Well, I forget the. All right, so step, the object, direction. All right, so. Let's just make it happen. So what I would do is I would just call this backward. My object is going to be model, new model. You want my direction to be equal to backward. Yeah, I think that's really all we need. I don't, I'll tell you what, I don't need to see my trace. And let's see what happens. So it actually converged on an optimal model He got rid of gender. He got rid of District A, District B, District C, and it focused on anxiety only as the optimal model. Now, this is exactly why I think back a couple of videos ago, this is exactly why we as humans with an understanding of statistics don't depend solely on R and computer software packages to make decisions for us. Because if you remember, we examined the residuals, normality of the residuals, and equal variance, some case-wise diagnostics, and we determined that using a linear model to predict exam score would not be appropriate. So anyway, that's the way a backward elimination model would work. Let me show you one thing too. If we were to put trace equal truth, this is actually not bad, especially in a smaller. What it'll do, it'll take you through what it does. It's what it starts. The AIC decreases and decreases, and so it continues to eliminate predictors because the AIC is decreasing, indicating a better model fit. All right, gang, that's all I got. We'll tie all this together in the final video. Take care.